And welcome to the video lecture for chapter 20 on the topic of sound. This is our second chapter covering waves and thus moving oscillations. Okay, so we have a lot of topics here, but we'll be covering some of them faster than others. All right, so nature of sound, origin of sound, where does it come from in the first place? How do we quantify sound in the air? Media that transmit sound, how they differ, the speed of sound in the air, reflection and refraction, those are definitely terms we want to make sure we understand. Energy in a sound wave, okay, because of course they do, it is an energy process, it is a mechanical propagation of energy. Then the idea of forced vibrations, natural frequency, resonance, a little quick review of interference, and finally the topic of beats, all right? All right, so let's get to it. All right, so sound is a form of energy that exists whether or not it is heard, okay? It's a lot like heat, all right? So our heat is the random motion of particles. Sound is very similar. It's a bit more orderly, but it does involve a lot of randomly moving very small particles, so it is rather than, kind of the macroscopic motion of just a few large objects, okay? So most sounds are waves produced by the vibration of matter, okay? So they're all waves, but they're mostly produced by the vibration of matter. For example, in a piano, a violin, or a guitar, the sound is produced by the vibrating strings. Okay? Okay? In a saxophone, it is created by a vibrating reed. All right? In a flute, by a fluttering column of air at the mouthpiece. Okay? So there's the vibration, the motion. In your voice, it's due to your vocal cords. All right? So the actual organ, the tissue is vibrating, thus creating that vibration, all right? And the sound wave that then propagates out into the room or space that you are in. So this vibrating material then sends a disturbance through the surrounding medium, usually air, in the form of longitudinal waves. So recall the two types of waves we discussed, transverse and longitudinal. Sound is by far the most important type of longitudinal wave. It's basically the only type of longitudinal wave that we'll discuss, whereas there's a couple of key transverse waves, mainly waves on strings and light are the really big important transverse waves, okay? But sound is longitudinal, which just means that its displacement is parallel to its velocity, all right? So displacement is parallel to velocity. That is what longitudinal means, okay? This just means parallel, okay? As far as range of human hearing, so, we're right here. We hear from about 20 to 20,000 hertz. Certain animals are specialized to hear much lower sounds, which are called infrasounds or infrasonic. Ultrasonic also applies to a lot of animals. They usually also have some overlap with the human auditory range, but cats, dogs, and certainly animals that use echolocation can operate, and their ears can pick up much higher frequencies, as high as 160,000 hertz, okay, which you can see is much higher than our 20,000 maximum auditory range. All right, so sound waves, okay? So they're vibrations made by the compression and rarefication. Remember, those are the terms that we used for gases in terms of the peaks and crests. You can think of a rarefication as a crest and a compression as a peak, if we're kind of drawing analogies to, say, like an ocean wave, okay? All right, so here's the idea. We could then create a compression by pushing a door open, thus compressing the air, forcing it out of this opening here. All right. On the other hand, as if we were to quickly close this door, then we now have decreased the pressure, and thus the rarefication is going to pull air in. Okay. So it's all about pressure. Compression is increase in pressure, and rarefication is a decrease in pressure. All right. Longitudinal waves. Sound requires a medium. It does not travel through a vacuum, so there is no sound in outer space. All right. But it also travels very well through solids and liquids, as including gases, okay? And in fact, sound will basically always be faster in a solid and faster in water than it is in air, all right? So how sound is heard from a radio loudspeaker, all right? So a radio loudspeaker is a paper cone that vibrates. The air molecules next to the loudspeaker are thus set into a vibration that matches the frequency of the vibrating paper. This produces compressions and rarefications traveling in the air, and the sound waves reach your ear, setting your eardrums into vibration. Thus, the sound is heard. Okay, so what about the speed of sound, right? You probably hear a little bit about the speed of sound. It's much, much slower than the speed of light. It applies to things about like the fact that you can see lightning before you hear the thunderclap. So what does it depend on, and what is the speed of sound? Well, it depends on wind conditions, temperature, and humidity. So the speed of sound in dry air at 0 degrees Celsius is 330 meters per second. All right. If there's a lot of moisture in the air, it will be faster. So the more suspended water droplets, the faster the sound will travel. And also, if the air is hotter, then it will travel faster. Okay, so warm air means faster. The colder it is, it will slow down. So in really Arctic sub-zero temperatures, we can have not too much of a decrease, but maybe something as low as 295 meters per second in a very extreme case. All right. And here we have an example that each degree rise in temperature above 0 degrees Celsius, speed of sound in air increases by about half a meter per second, or more precisely 0.6 meters per second. Speed in water is about 4 times faster than the speed in air. And in something like a metal like steel, it's 15 times faster because those denser materials are able to propagate the wave much faster. The molecules bounce into the next set, or in the case of a solid, that crystalline rigid structure of the solid is able to transmit that wave many times faster than in the gas, which makes sense because the collisions in the gas are going to be more prolonged, right? Okay? All right, so let's do a check here. You watch a person chopping wood and note that after the last chop, you hear it 1 second later. How far away is that person? All right, well, if it takes sound, a certain amount of time to travel, or it takes 1 second for sound to travel a distance and it travels at 330 meters per second, that means they must be 330 meters away. Okay, so you hear thunder 2 seconds after you see a lightning flash. How far away is the lightning? And this is something people always, every time you talk to somebody during a lightning storm, everyone's trying to remember the rule. Well, here you go. All you need to remember is the speed of sound. It's 330 meters per second. Thus, if it's a 2 second delay between seeing, because the light essentially is instantaneous for all intents and purposes, it really truly is so much faster, then when are you going to hear it? Right? That means it is 660 meters away because it takes 2 seconds for sound to travel 660 meters. All right? So it's about 3 seconds per kilometer. Okay? About 3 seconds per kilometer. All right, so now some key properties that apply to all waves, but are particularly applicable to sound. All right, although we also will discuss them in the context of light later on. Reflection and refraction. And let's start with reflection. So reflection is a process in which sound encounters the surface and is returned. It's often called an echo. So an echo and reflection are interchangeable terms. And multiple reflections are called a reverberation because it's bouncing back and forth. So here we see sound waves represented as rays that are bouncing off of a wall and then getting retransmitted, all right? And the law of reflection says that this angle must equal this angle, okay? So reverberations are best heard when you sing in a room with, think about it, you want the sound to bounce off, so you want hard surface walls because you want as much energy to be returned from that wall rather than absorbed by the wall. And a soft surface, like a carpeted wall, will absorb that energy, thus the actual amplitude of the sound will diminish significantly. All right. So consider a person attending a concert that is being broadcast over the radio. The person sits about 45 meters from the stage and listens to the radio broadcast with a transistor radio over one ear and a non-broadcast sound signal with the other ear, right? An uncovered ear, in other words. Further, suppose that the radio signal must travel all the way around the world, so bounce on satellites at the speed of light to get back to the ear. All right? So, which signal will be heard first? The radio signal or the non-broadcast actual sound traveling 45 meters? Which one is it? This is just to highlight how much faster light is, all right? The same time, because it turns out that the radio signal is traveling at the speed of light, which is 300 million meters per second, or 3 times 10 to the 8 meters per second, because that's 300 million, since 10 to the 9 would be a billion, all right? So 300 million meters per second, and then sound travels at a measly 300, well, if we're so it's always easy to compare sound and light, because you can think they're both 300. One is 300 million meters per second, and the other is just 300 meters per second. Now, of course, sound more accurately is about 340, at least in room temperature air. And so then we have a time, both approximately, it's not exact, of about 0.13 seconds. All right, pretty cool. Okay, so now what about refraction? Okay, so we got reflection, which is a wave bouncing off of another surface, like a sound wave. Refraction instead is the bending of a wave, all right? And it's caused by a change in speed. So as you think of a wave is composed of these wave fronts. And if there's a condition that varies along that wave front, then that means that the whole angle of the wave front will change. Thus the direction of the ray, which is perpendicular to the wave front, will change accordingly. And that allows sound to bend. It also applies to ocean waves refracting through, through certain, like different conditions in the ocean. It applies to light refracting as it moves from one medium to another, like from air to glass. So refraction is a property of all waves. In the context of sound, it's particularly pronounced when you have cool air and warm air, because what's going to happen is the sound travels slower in the cool air, which means that the waves will bend towards the cool air. Since the sound travels faster in the warm air, the waves then become more compressed on this end, thus that just contributing that much more to the upward bend. All right? And of course, if you reverse the direction, then the sound will still bend towards the cool air, but that would then cause the sound to bend downwards. Okay? All right, so you see how that works? All right? So temperature vibrations or variations can create a big change in the refraction of sound. Wind as well. Okay? So when air near the ground on a warm day is warmed more than the air above, sound tends to bend. All right? So we have a warm day. The ground is warmer than the air above, so that means that the sound will bend upwards, away from the warmer air towards the cooler air. All right, so in the evening, when the air directly above a pond is cooler than the air above, sound across a pond tends to bend, all right? It will bend downwards, okay? And so that means that the sound is actually kind of forced along the water and that energy hasn't dispersed as much. And so that means that sound in the evening will travel very well across a body of water, like a canal or a lake or something. And so you can hear sounds very well, better than you would otherwise at such great distances or relatively large distances. It's an interesting effect. I don't know if you've ever noticed it. Now it applies to particular times. In this case, this is the air being cooler above the water. If you think about specific heat of water, it depends what part of the evening you're in, because of course at some point the air above the water actually might be warmer because if the air is cooled off more quickly. But this would be kind of immediately after, maybe immediately after sunset, or maybe like right at twilight when you have the air is still warmer than the water. Okay. Okay. So multiple reflection and refractions of ultrasonic waves can lead to an application of sound like an ultrasonic. All right, so this is bouncing off and then using detectors to find out the exact rate at which things are bouncing, basically the time it takes for waves to bounce back, and then we can get really complicated images like this one. Okay. Also, dolphins can use the reflection of waves as a way to ascertain their environment, to find out what's in front of them. Bats do it as well. Okay. All right. So what about a forced vibration? Okay. So a forced vibration is setting up a vibrations in an object by a vibrating force, some external force. So a factory floor vibration caused by running of heavy machinery, right? That's a forced vibration. Or you like sitting at a table and just shaking the table. That would be a forced vibration. Okay. Now, why bring up something like that? Well, because forced vibrations are interesting when you compare them to natural frequencies, because this vibration has some frequency. That would be the frequency of the forced vibration, the forced frequency. Okay, well, objects based on their materials, their densities, the distributions of density, and their size and shape have particular natural frequencies. Sometimes they'll have one, and sometimes many natural frequencies, all right? And it depends on all kinds of parameters, elasticity and shape being the important ones. So then if you think about it, if the forced frequency matches the natural frequency, then you get something called resonance. All right, because now you're putting in just the right amount of energy in the right form in order to get the maximum amplitude vibration. Okay, so a phenomenon in which the frequency of forced vibrations on an object matches the object's natural frequency. So swinging in rhythm with the natural frequency of a swing. All right, so obviously you can swing in a way where you're not getting higher, right? But if you match the natural frequency of the swing, then you get higher with each leg pump. Okay, all right, I think at a playground. Tuning a radio station to the carrier frequency of the radio station. Okay, that's what's going on when you tune in. Troops marching in rhythm with the natural frequency of a bridge, which is not a good idea because that means that with each subsequent stomping of their feet, they would then cause a bigger and bigger amplitude that would just continue to grow, right? Maybe causing damage to the bridge or even breaking it. Okay. Here's a dramatic example of wind-generated resonance. So in this case, the particular wind in this valley in Washington state matched the natural frequency of the bridge, and then on a particular windy day, the bridge just tore itself apart. I mean, of course, you could think, oh, well, the wind tore it apart, but really the only reason the wind was able to tear it apart is because every time the frequency of the wind hit the bridge just then fed on that frequency at resonance. Okay, so it's not incorrect to say the bridge tore itself apart. All right, and that's why you want to make sure that you don't have natural frequencies in bridges that are anywhere near any of the external frequencies that are common in that area, such as the ones in this particular valley. Okay? All right, so interference. We've talked about this before, so a quick review. We've seen this figure. It's the idea of constructive and destructive interference. All right. So interference is a property of, or we discussed before, both types of basically any wave. All right, here are ripples in the pond. Now this is a new representation of interference, okay? This is really kind of showing a good summary of, if you imagine like interference of a light wave or any transverse wave, like a wave on a string, you add them together, you just get a bigger amplitude. But look at how it look for sound. In the case of sound, bigger amplitude takes the form of more compression and more rarefication. So in other words, the pressure is greater here. So this would be P large pressure, and then you have a very low pressure in the rarefication. More dramatic in terms of the large pressure and the low pressure than you would when the wave is not being constructively interfered. All right, and then of course cancellation for something like waves on a string means that the wave is just flat because the two waves traveling in maybe opposite directions are canceling each other out. Or you think of two sound waves that are passing through each other, and the effect is as if the air had no sound traveling through it at all. The molecules just are at rest because they're essentially, the two effects of the waves are canceling out. Okay? So an application of sound interference, now that we've reviewed it, let's discuss a new application. Destructive sound interference in noisy devices such as a jackhammer that are equipped with microphones to produce mirror image wave patterns fed to the operator's earphone, thus canceling the jackhammer sound. So essentially what happens is in any type of noise canceling earphone, the ambient sound is recorded, especially if it's a continual ambient sound like a buzz or a jackhammer motor, or like a banging sound. It's recorded and then played as a mirror image, which is in other words a slight phase shift, and thus when it's played back into the person's ears, it cancels out the original sound. Okay? So it's a really sophisticated way of canceling out noise. You're not just muffling the noise, you're actually canceling it out. All right? So application of sound interference in stereo speakers, out of phase, sending a monaural signal, which is just a one-tone signal. One speaker sending compressions of sound and the other sending rarefications. And then the effect is that they're going to be canceled out, right? The sound is diminished. It's as if the sound went away. The speakers are still on, but the sound is practically gone because they're basically, because they need the two waves to arrive basically at the, you could match up distances here and have the same effect, but when you have them right next to each other, you know that the waves are essentially arriving in the same place at the same time, but exactly out of phase. Thus, cancellation, no sound. Okay, now beats. What are beats? We're not talking about kind of the musical terminology, we're talking about the physical meaning of beats, although there's a relationship between the two. What they are is a periodic variation in loudness. All right, and it's due to interference, but instead of sort of spatial interference like here, where it's all about the proximity of the speakers and the way they're canceling out due to the out of phase sound, this has to do with two sounds of different frequency, okay? And since they have different frequency, that means that every so often their peaks, or maybe you think of them as their compression zones, are going to match up. They're going to they're going to occur simultaneously, but that's only going to happen every so often, all right? So it occurs with any kind of wave, and what it does, if we think of the sound kind of traveling out continually from these two tuning forks, and these are tuning forks of different frequencies, so you think of them as frequency 1 and frequency 2. So as the two frequencies come out, all right, and also then two different wavelengths represented here, right? So this one has a shorter wavelength, wavelength 1, and then wavelength 2 is longer, all right? And if wavelength is longer, then frequency would have to be lower. And so then because the speed is the same because they're both traveling through air. And so as the two waves come out, notice every so often their crests are going to line up, and that's going to create a momentary loud amplitude sound. But then if you were, imagine you're standing here letting this sound wash over you, and so every so often they're going to be loud, but then every so often they're going to be totally silent because the two sounds are going to cancel out. And then there's going to be in between. So the effect is going to be like, that's what we mean by a beat. It's getting louder and softer. And the tone would just be the average of the two tones. So if it was a higher pitch, it'd be something like, And if the frequencies are very close together, then then you could have it be, kind of, so if they're only 1 hertz apart, then the beat would occur with a frequency of 1 hertz. If the frequencies are, say, 5 hertz apart, then there would be 5 beats per second, which would be hard to do, right? And so really this is most noticeable to the ear if the beats are either a fraction of a hertz apart, so that the beat frequency is, say, once every 2 seconds, or at most maybe 2 beats per second, okay? So piano tuning is a great way to apply the idea of beats, because you can get a particular tuning fork that has a certain frequency, and then play the key on a piano and see if it does create that sound, that wobbly sound, that wow. Because if it does, then your piano's out of tune, right? Assuming your tuning fork is perfect, and then you can, fix it until you don't hear that, okay? All right, so that's it for our introduction to sound. All right, well, thank you so much for watching this video, and stay tuned for the last video on vibrations, all about musical sound.